Okay. So what we're going to, oops, put my screen on. What we're going to look at today are what you're asked to do in section 9.1. And basically, one of the things, the first thing you're going to do is check to see if a given solution works. So if a given solution to a differential equation works. So you're going to be given a differential equation. You're going to be given what they believe is a solution, and your job is to check it. So they don't tell you how they got the solution, they just got lucky or whatever, but they got a solution, and it's your job to check it. So an example of that would be question 1. The differential equation is y dashed plus 4y equals 4e to the x, and the solution, or at least the possible solution, is that y equals 4/5 e to the x plus e to the negative 4x. So our job is to check that that works. How do you think you check that that is a solution to this differential equation? By the way, it's a first order differential equations, as we mentioned yesterday. How could you do it?
Integrate it?
Oh, you could try and solve it, but since all the hard work is done for you, there's an easier way to do it. Couldn't you just differentiate that, put it in here, take 4 times of this, put it in here, and if the answer is that, it works. Isn't it basically like substitution, right? Plug and chug. So first thing I need to do is find out what the derivative is. So instead of integrating, which is what we kind of did yesterday, and try to solve it, here we're not trying to solve it. Here we're told what it is. We're trying to check that it works. It's a slightly different process, right? Well, if you differentiate this fella, you get that. Now, if you differentiate e to the negative 4x, and I've got my differentiation hat on, right? Differentiation. If you differentiate e to the negative 4x, you get e to the negative 4x times something else. What's missing?
Negative 4.
Are you all happy that that's what y dashed is? Okay, now, the differential equation says y dashed, which is this. Right, so that's the y dash part, plus 4 lots of y, which means plus 4 lots of this, which is not the same thing as y dashed. It's a little bit different. If this works, shouldn't all of this equal that? So what I'm going to do is multiply this all out, collect like terms, and if things turn out good, it should equal that. So let's see what we have. 4/5 e to the x, take away 4, e to the minus 4x, 4 times 4 is 16, so it's 16/5. 4 times 4 is that guy. This fella kills off this fella. If you add these together, you get 20/5. But isn't 20/5 check? Does that make sense? That this actually, I've now proved that this is a solution to that. What's the analogy of that? Can you imagine someone gave you a quadratic equation and says, check that x equals negative 4 works. Don't you just plug in negative 4? It works, right? Isn't that kind of sort of what I'm doing here? Right? I got a solution, they tell me it, I'm checking that it works, right? So we're not solving equations here. We're just checking that one that they tell us works, right? It's a little different. We will eventually get to solve our own, but right now, that's not what's happening. Let's see if I can find another one of those check things. I'll go right into question 2. We have to check that this function, the one I'm writing down, is a solution to a differential equation that I'm going to give you in a moment. Right, that's it. And we have to check that this one works. And the differential equation is this fella. So I'm going to check that this works for that differential equation. I'll have to do some intro work. I know that y is this. At least I've been told it's this. And I need to find out what dy by dt is. And then I can start substituting things in. Well, if you want to do this fella, would you agree that it's a product rule? So we're back to Calc 1 world, right? Differentiating two things multiplied. So it's going to be f dash g plus f of g dashed. And differentiating negative 8t just gets you negative 8. That guy is negative 8, leave the second guy alone, plus leave the first guy alone. And if you differentiate a cosine, you get a negative sign, and you still got that minus 8 at the end. And let's make it look pretty neat. Negative 8 cosine t's plus 8t sine t. Take away 8. Okay, so that's just what the derivative is. Now I know all the pieces. I'll put them in here and see what we get. So it's t dy by dt has to equal that guy. Well, t times all of this. Has to equal a y, which is this guy, plus 8t squared sine t. Right, let's FOIL this out and see what we get. I get negative 8t cosine t. Then I get 8t squared sine t. And then I get negative 8t. And on this side, I guess if I take the brackets away, because we don't really need them now. You would get that. Would you agree that the two sides are the same? They might be in slightly different order, but they're the same things. Right, that's us checked that it works. Now, if they'd phrased the question a little bit differently, instead of check that it works, and said, does this work as a solution, right? The answer would be yes. But can you imagine a situation where one side wasn't the same thing as the other? Wouldn't that be a no then? It doesn't work, right? That's not a solution. Now you might think, well, how am I going to do any of this in WebAssign? And the way WebAssign does it is it asks you to find the right-hand side, and you put it in a box. Then it asks you to find the left-hand side, right? This guy here, and you put it in a different box, and then you merge them, right? So that's kind of how it gets you to do it, right? You take whatever this comes to and you write the answer down in a different box, whatever this comes to. And I think whatever, yeah, they basically lead you through the steps that I did. Okay, so that's our second example of check that this is a solution that works. Are we comfortable with the process? We good? Okay. So let's change tack a little bit. Not going very far. On to question 3. And it says, interesting kind of question, for what values of k satisfies, oops, sorry, miss scroll. So for what values of k does y equal the cosine of kt satisfy the differential equation 16 of these guys should equal negative 49 of that guy? So we're not just being asked, check, does this work? We're being asked to find for what values of k does this work? And they take you through a whole set of working, but I'm going to do my version. I'm going to start off with that piece of information. And I'm going to find its second derivative. And once I know it, I'm going to do 16 of them. And it better equal minus 49 of them. And then we'll figure out what this, for what values of k that'll come into. Now, be really careful about this. If you differentiate the cosine, you do get a negative sign of kt times something. What's missing?
K.
Yeah. It's a bit like if somebody said differentiate cosine 2x, wouldn't you get minus sine 2x times another 2? So you get a 2. Now, once you've sorted that out, if you differentiate this fella, you do get negative k cosine kt. But don't you also get times another k? So are you happy where that k squared is coming from? Is that okay? Now, the differential equation says that 16 of the second derivative is equal to negative 49 of the original function. So 16 of these guys needs to be equal to 49 of the original guy. Now, if I distribute this, I get negative 16 k squared cosine kt, and that's negative 49 cosine kt. Now, eventually, I'm going to be able to tell you what values of k does this work for. Let's tell you what I'm going to do first. I'm going to divide both sides by cosine of kt, essentially making it go away. Now, as long as the cosine of kt isn't 0, that's allowed. What do you think I'm going to do next? Remember, our goal is to find out what k needs to be for this to solve. What do I do next?
Divide by negative 16.
Agreed. Which you probably don't need this line, but since these are notes, I'm going to put that line in. Right, it's probably as I say. Now, what's going to happen next?
Take the square root of both sides.
Now, when you take a square root, there is two possibilities. A lot of people forget the minus. What that gives me is plus 7/4, and the other one is negative 7/4. Do you see that's the two k values that we were hunting for, right? For what values of k does this work, right? Are we good? So it's not really like 1 and 2, although it's kind of similar, isn't it? You do a lot of the same things, but at the end of the day, isn't this a little bit different because you actually solve for some missing variable, in this case, k's. In the others, you just checked that the left ended up being right and you were good to go.
Sorry, for the last example,
Yes.
second line, you just divided the cosine.
Yeah, I basically divided both. Well, yeah, I divided both sides by cosine t. You can do that as long as you assume that the cosine of kt isn't 0. If you're a purist, I would bring them both over and take it out as a common factor and then get rid of it. But that's 2 lines and I don't want to do it. Is that okay?
Yeah, thank you.
Yeah. Now, I'm going to show you what the homework questions look like. Oh, Drew Madison never made it. This is some different homework questions from that section. Oh, I'm going to close this for a minute because that's kind of loud. There we go. And then I'll go back. Right, make it a little bit bigger because some of your screens that you use aren't that large. Okay, that's really big. Now, in question 4, it says, which one of the following functions are solution to this differential equation? It's a second order, right? Y double dash plus y should equal sine x. And you pick one, that one, and you try it. And if the left-hand side ends up being sine x, you use it. And if it doesn't, you don't use it. But it goes and says, select all that apply. What that means is, and I guarantee it virtually, that there are going to be 2 or 3 that work, which really means it's a big question. Because don't you have to do the process, what, 5 times? 2 work, 3 don't? You know, something like that. 3 work, 2 don't, whatever. I don't think they did it, but I can imagine all 5 working, right? So you go and you check each one. You could check that one, for instance, or you could check this one, or that one, or that one. And if it works, you keep the little check marks on it. So I'm going to pretend I know the answer because I don't. Those 3 work. That's what your answer would look like, right? Don't quote me because I guarantee that's probably wrong, right? Is there any one of those 5 that you'd like me to do just to show you the process of how you would check it against this differential equation? Or do you feel comfortable you know what to do, it's just going to take you time?
Let's do the third one. The y equals x sine of x minus 6x cosine of x.
Yeah, that's a good choice. Would you agree that's the ugliest looking one of the set? While I'm at it, I'll write down what the differential equation is because that's going to disappear in a second as well. Any gut feelings? Do you think it's going to work or do you think it isn't going to work? We've got a couple of shaking heads, so that's my gut feeling. I've been proved wrong tons of times, so I might be proved wrong this time as well. Oh, I need to find the first derivative so that I can then find the second derivative. Except, haven't I got 2 product rules? So that's not going to be easy, you know, it's going to take some work. So f dash j plus f of g dashed and f dash j plus f of g dashed. So you get 1 times the untouched sign plus x times the derivative of the sign. That's the first chunk. I'm going to call the negative 6x f. That way I don't need to worry about is it plus or minus. F dash is negative 6, leave the other untouched. Minus 6x times the derivative of a cosine gets you a negative sign, so that ends up being plus. And I get that. And I'm looking for anything that might combine. And of course, nothing combines because it's just not one of those days. Right? If you differentiate a sine, you'll get a cosine x. If you call this f and g, you will get another product rule. This one I'm just going to do in my head. 1 times cosine x minus x sine x. This one you'll get eventually positive 6 sine x because 2 negatives make a plus. And this one is another product rule. F dash g plus f of g dashed. Now, does anything in this mess work? Well, that guy and that guy gives me 2 cosine x's, and that guy gives me 12 sine x's, but not much else. So that is the second derivative. I'm going to add y. I'm going to add an x sine x and a negative 6x cosine x. So this guy, right, the second derivative, plus this guy. Let's see what we get. What do we get? Well, this cancels out with that, and this cancels out with that. I get 2 cosine x's plus 12 sine x's. So those who thought it failed were right, because shouldn't it equal sine x if it works? Okay, that means we know one of them that doesn't work, right? The third one. But there's still 4 guys out there, right? And I'm pretty sure at least 2 of them will work. Might be more than that, but at least 2. Are you comfortable with how that type of question is done? Right? They give you, it's basically the same as the first questions we've done today, but you do it 5 times now rather than just once. And some of them do work and some of them essentially don't work. Checking my time here. Here we have a function y equals log of x plus c over x. And we're being asked to prove that it solves this differential equation. So essentially, don't I need to find the derivative? Plug it here and show that all of this equals 1. Okay, save some space. I want to differentiate that and put the answer here. What rule from Calc 1 do you use to differentiate a fraction like this? You might have forgotten its name, but do you know the technique?
Quotient rule.
That's the guy. So it's f dash g take away f of g dashed over g squared. So if you differentiate the top, the derivative of a log is 1 over x. The derivative of a number, because plus c is just an unknown number, is nothing. So that's all you get from f dashed, multiplied by g. Take away the f, which is this guy, times g dashed, which is 1, all over x squared. Well, they multiply together and you get 1. This guy and this guy. So there's y dashed. Right, I'll plug it in here. I get x squared times y dashed plus x times y. These cancel out and you get this. These cancel out and you get this. And these cancel out, and you're left with 1, which is what it should be. So it does work, doesn't it? Now, the next bit goes in and it says illustrate several members of the family of the solutions. And that would take a long time for me. It's not hard to do, it would just take me a long time to do it. So let's cheat and show you what it looks like. I'm going to have to shrink this way down. There are 4 pictures here, 2 in the top, 2 in the bottom. Now, the guy that we are looking at is this function here. Do you see the log x plus c over x? Now, what they mean by several members of the family on a common screen, you basically go to your TI-84, right? And you plug in what this function looks like, plus 0, plus 1, plus 2, minus 1, minus 2. So you just replace the c with numbers like 0, 1, 2, 3, minus 1, minus 2, minus 3. And when you do that, right, you will end up with a bunch of guys that look like that. So I've already set this up and I didn't realize that I'd set it up with another class. So I can actually show you it on my calculator. That's just 3 of them. If I hit y equals, can you see the guys with the various numbers on it? And so the picture I chose was picture 4 because that's what it looks like. And that's how you choose the right one. So we now have a solution that has a funny look to it. This is called a general solution to the differential equation, right? That's the name we give to these guys. Why is it a general solution? It's got a plus c in it, right? Now, in question C in that same lot, you're being told y of 1 equals 2, and they ask you to essentially find C, find the particular solution. Now, when they write this down, they mean when x is 1, y is 2. So I'll go up here and I'll say make y 2, make x 1, and you got that. If you tidy it up a little bit, isn't the log of 1 0? So 0 plus c is c, and isn't c over 1c? Isn't c 2? Which means that your answer now looks like that guy. And we call them particular solutions. So your answer will be that fella. Now, they make a harder version of that one, because that one was pretty easy. And I don't want people to get into the bad habit of thinking C is always this number here. Just because a lot of the time it is doesn't mean it's going to be true all the time. So here's the last one. Y of 2 is equal to 1. So y is the natural log of x, add c over x. And if you're told this piece of information, 1 goes here, the natural log of 2 plus c all over 2. A little cross multiply. And then subtract log 2 from both sides. Do you see in this case, the c is quite an ugly looking thing?
Sorry, do you mind moving your page up a little bit?
Sure.
Thank you.
But do you see in that second example that the c wasn't a nice number? It certainly wasn't 1, right? It's this, which means that our solution will be log x plus c over x. And are we good? Okay, nods it is. Let's look at another situation. This is a graphical or a visual situation. And this one is like question 6. The rate of change of a population with respect to time. So how many more people will live in that town a year from now? In this formula is given like this. Not that you need to know this, but I happen to know this differential equation because it's a very frequently used one. It's called the logistic model for population growth. It's actually a much more realistic model than the exponential model. Remember the exponential model where the population would increase and then it would shoot off to infinity. And if you used it to predict how many people would live in Seattle in 100 years, you get the ridiculous answer that everybody in the universe lives in Seattle, right? Because the answer is 22 trillion. And the reason for that is that the exponential growth model, which is what that's called, is really good for 2 or 3 years, but it's not good for long-term prediction. The logistic model, however, is very good at predicting population growth models, right? How many people will live in Seattle in 10 years from now, or even 100 years from now. It's pretty good at predicting long-term numbers without going crazy. So back to the question. The rate of change, that's a derivative. Tell you some information. If it's a positive number, doesn't that mean that the population is increasing? Because this is just telling you how many more or less people, right? A positive derivative means next year there's going to be more people in Seattle than there was last year, or more rabbits on the island than there was last year. Of course, if it's negative, doesn't that mean that the population will decrease? What does it mean if it's 0? What can you say about the total population?
Not changing.
Correct. So it stays the same, or not changing is fine. Right, back to this question. It looks impossible, but it's not. For what values of P, the population, is the population going to increase? So essentially, aren't I trying to solve this? Agreed? Which means I'm trying to solve this. And then I'm going to make a non-mathematical assumption, but it's a common sense assumption. Would you agree that P, the population of rabbits or people in Seattle or whatever it is, doesn't it need to be a positive number? You can't have -10 people or -10 rabbits, okay? Now, since it has to be a positive number, won't all of this be positive? Right, if P is positive, right, the population is positive, won't 1 times P, this piece here, just talking about this piece here, is positive. So don't I need to only look at what values make this positive? So I've actually made my job a little bit simpler by just trying to figure out what makes that happen. Now you could do it mathematically, but I think you could probably just look at that and figure it out. Would you agree it's got something to do with 4,000? Does it have to be bigger than 4,000 or less than 4,000 for this to be positive, the whole thing?
Bigger.
So if this is bigger than 4,000, what will this fraction become? Bigger than 1? And isn't 1 take away something bigger than 1 negative? Agreed? So bigger than 4,000 doesn't make this whole thing positive. Right, we've made the assumption that you must have at least people, right? So 0 on one side. But more importantly, do you see why I chose 4,000? As long as you're less than 4,000, won't this fraction be a positive number? Pick 2,000, right? 1/2. positive, right? Pick 3,000. 1 over 1 minus 3/4. That's a quarter. That works, right? Pick 3,999. Won't that be 1 take away a tiny number, just shy of 1, but shy enough to make the whole thing still positive? So that's for increasing. I won't do any math for the next one. What value of P do you think the population is going to be decreasing?
Greater than 4,000?
And I don't know what the word is, and I guess I could look. I'll just call it stable. Stable means it doesn't change, right? Actually, doesn't change would be better. Would you agree that that is when it is 4,000? Right, when the population is 4,000, won't the derivative be 0? And a derivative of 0 is not changing, right? Stable population. Now, what the logistic model does is it says, look, Seattle, an island with rabbits, whatever the story is, there's only so many resources, right? There's only so much square footage or water or whatever it is that matters. And so the biggest it can ever be is 4,000 rabbits, right? And what the model does then, it predicts what the future populations will be. Now, if they get too many rabbits on the island, won't they eat all the stuff? And next year, a lot of them starve to death and the population fixes itself and it ends up reducing back to that magic 4,000, right? It's called the carrying capacity in the jargon. It's very useful because the government, when they issue rules about how many deer you can shoot, how many salmon you can catch, how many halibut fishermen can catch, they might think, well, isn't that random? Don't they just decide, we'll let them shoot this many this year because we want to? No, they actually use a number, which is basically whatever the amount over the carrying capacity is. So if they say this forest should have 7,000 deer in it, and we've got 8,000 deer, we know that because we've basically counted them, that will allow them to put 1,000 licenses out, right? You can shoot 1,000 deer in this forest. And the reason that doesn't have any effect on the population is because if you just let nature take its course, wouldn't you have too many deer and they'd eat too much and they'd starve and there'd be a glut and then a famine, right? The population would just bounce around like a yo-yo. So they're basically just taking over the job of the predator. And if you do it right, you can actually kill deer forever, can't you? Just take it to carrying capacity.
I have a question about P. Does P have any units, or is it just is there a number that factors
it's people,
in?
So it's like if it's 200. This is it's a population, so it's rabbits. Let's do rabbits on an island. So this would be if there's more than 4,000 rabbits next year, the population will go down. If there's less than 4,000 rabbits next year, the population will increase. If there's 4,000 rabbits next year, the population will be stable at 4,000. And the reason why it's stable is every year, don't some rabbits die because they get eaten or old age, and don't baby rabbits get born, right? So what they're just saying is, what's the change in the population going to be? And it's not like square meters are in it, it's just a thing. 2,000 rabbits, 2,000 people, whatever the number happens to be.
That makes sense. Thank you.
Okay, now, God in Himmel, do we get time for one more? No, that's the same guy. Okay, one last question to do. I'm going to do a visual one. So it's from the homework, and it's a picture. And that's all we'll have time for today. We almost got to the end, but that's fine. We'll finish it tomorrow. Here is a differential equation. I wish they'd called it dy by dx, but no big deal. Do you see t is like the x-axis, right? So if you think of it as dy by dx, it works. The derivative is this. And this guy and this guy could have been the solution, but they're not. And we're trying to figure out why it's not. Well, e to the t, y minus 1 squared. And the trick we use is that this here says that the slope of the curve that's a solution, right, has to have some properties. Here's the first one. Would you agree that e to the t is a positive number no matter what t is? E to the 2 million, e to the negative 2 million. Right? E to the negative 2 million is tiny, but it's still positive, right? Would you agree no matter what the y coordinate is, isn't y minus 1 squared positive? So my conclusion is that this derivative is always positive, or it might be 0, but nothing else. Which means, shouldn't the curve be an increasing, a going uphill curve? Can you see why this one fails? Do you see it's going downhill at the end? So this function is increasing and decreasing, but the derivative of this is greater than or equal to 0, implying that the graph of the solution to this differential equation cannot be decreasing on any interval. So you're basically putting into words what I just said. See how that work? Right. Now the second one is trickier. This one here also doesn't work. Well, if I look at it, you say, but it's increasing. And I agree, that's not the problem. There's a less obvious problem. Back to the differential equation. When y coordinate is 1, right? When y is 1, won't this derivative be a 0? Right? When y is equal to 1, won't this be 0? What does a 0 look like, derivative look like on a curve? Little horizontal,
Flat. Yeah,
little
horizontal.
flat line. In fact, isn't that roughly on this graph, isn't that where the flat line should be? Does this one have a flat line at 1? No. So that's why this one doesn't work. So this one has increasing, but it isn't horizontal at y equals 1. This one is horizontal at 1, but it isn't increasing. Do you see each one had one of the pieces wrong? Just a different piece wrong. So